All right, everyone. So I think I can start it. Hello, everyone. Thanks for coming. My name is Shaoxuan, and I work for Alibaba Group. Today the talk is about streaming processing. So in streaming processing, it's used only to provide a lower level API like Storm. So it's good, it's flexible, but it's set a very high bar. A lot of users they don't know how to program in Java, Scala, so they cannot use it. But the good thing is a lot of modern streaming computing engine like Kafka and Spark, they support SQL. Kafka has KSQL and Spark has Spark SQL. But unfortunately, those SQL for streaming, they didn't follow the ANSI SQL, so it has different semantics. So our goal is to make the streaming processing towards ANSI SQL, because once we've done this, we will unify the batch and the stream processing. So this is what I'm going to talk about today. A little about me. I graduated from UCSD and work for Broadcom, Facebook. And 2.5 years ago, I joined the Alibaba Group. Now I'm leading the SQL engine team for the Flink engine. So the Flink team works very closely with the Apache Flink community. We have 6 commuters, and 3 of them working on the SQL in my team. All right, so this is an agenda. Basically, I'm going to first introduce and explain why the ANSI SQL makes sense for the stream computing. And we need to derive some semantics to make it happen. And then dive into the Flink SQL engine, including the architectures, features, and the performance tunings kind of thing. And at the end, we'll introduce the optimization works we have done to make it power enough in the world first class performance SQL engine for the stream computing. Okay, let's first look at the ANSI SQL for stream processing. So the first thing is why SQL? So everybody talking about the SQL. Different data processing engine now support SQLs. And IBM even claimed that, or they proposed that SQL the world, right? So everybody talks SQL. Why SQL is matter? There's might be a lot of different reasons. From my point of view, there are major 5 reasons. First, SQL is widely used, right? And people understand the SQL. It's very easy to read. And secondly, SQL is declarative. It has been proven sufficient enough to describe the user business logic. User just need to describe their query. They don't need to care about the implementations. And then there's optimized. SQL has an optimization framework. It can automatically, whatever your query is, it will optimize the plan. And then SQL also is stable. It's more than 30 years. It's never been have the big change, regression. So SQL API is very stable. And the last is most important part is that we want having the SQL to describe the stream processing, because once we've done that, we will have one query, the same result. So that's the reason for SQL. So SQL is very promising, and but how does it make sense for the streaming? So SQL works for the batch processing. So let's first compare the batch and the streaming. In batch processing, so it only compute the result once. When to receive all the source, gets one result. But in streaming processing, it's much more complex. So user want to know the result as soon as possible. When any record comes in, it wants to see the result. So in streaming cases, it's more challenging because you have to emit the result as soon as possible. We call this as early filing, right? So you have to file a result. On the other hand, when you file a result, you don't know what's going on, what will happen afterwards. So you might need to update the result. So you have to update the result you have already filed. You have to refine the result. So it's very common in streaming processing that it emits the intermediate result. It's not the final result. You just emit whatever you have and keep refining, updating the result to ensure the correctness. So that's a major difference we have observed. So in other words, we need to answer several questions. Take care of those questions such that you can describe a streaming processing. So the first question is what and how the results are calculated. So this is nothing, right? It's purely the user business logic. It's same as batch processing. You can using the SQL describe for the batch, and it also can fully describe, the stream compute can fully describe by SQL also. The other two questions is when to emit the result. So user need to tell the engine when and how frequent the result should be emitted. So this does not affect the also user business logic. It can be integrated as a job conf. For each job, user just specify, okay, this is a result. This is the result latency SLA. And the last one is how to refine the result. So there's multiple ways to refine the result. Different engine has different ways. So like Spark and Kafka, it's let the user to refine the final result. In our point of view, for the user experience, better user experience, it's better to refine the result inside the SQL engine. The user shouldn't need to care about the refinement. They just describe their business logic. Then the SQL engine does the refinement automatically. Once we understand this, we realize that, okay, stream processing can be described by the ANSI SQL. We do not need to introduce any streaming SQL. Good. But how does the SQL make sense? The SQL was applied to the table. Streaming even doesn't have the table. How does it make sense? We need to derive the definition for the table for the stream. So in batch processing, table usually is immutable and static. In the streaming, the data keep changing. So based on this, we propose a dynamic table. So basically, the stream comes in, we apply the data to the table keeps changing, and we can derive the change as a changelog to the stream. The analysis behind this dynamic table is stream table duality. So basically, you can imagine that at any given point, you can receive a stream and apply to a dynamic table and derive the changelog directly to another stream. And those two streams are exactly same. So that means the stream and the table has the same information. Information has not been lost. So stream table duality. With stream table duality, anytime when you apply a SQL, you actually apply the SQL to the dynamic table. So for instance, when you have a stream, you can view it as a dynamic table, and you do the continuous SQL query, and you get another dynamic table, and if you want, you will have a stream out. You might remember that the table here is not materialized. It's just something in your mind. When you do the queries, those tables not existing at all. You just view the stream as a table. For instance, if you want to do the input stream, do the query, let's say the input stream has two columns. One is the username, and the second column is URL. If you group by the username and count the URL, you basically have two tables. The left table is input data. You have two columns, user and URL. It's a pan table. And once you do the grouping aggregate, then it has two columns. User ID as a key and the count as a value. So when you keep receiving the data, you basically changing the dynamic table as a result. And if you receiving the second Mary here, instead of having another row, it's just update the previous row. So the result here is the update table. So this is what I have mentioned that we need to refine the result. In this case, refine the result is simple because the result, whatever when you're counting the URL for the Mary, it's just updating the result table in the same row. And then let's say Lizzie. You're updating the result for the Lizzie, and then finally you update for Mary. Every time you're just updating the final table. So this is an easier refinement. But unfortunately, refinement could be very, very complex. For instance, in this case, it's also refinement. In this case, we do the word counting. Once we do the word count, we do the frequency count. That means the example is that when you're reading a book, on the first page you have 3 words, hello word and the bark. So these 3 words only have appeared once. So in the intermediate query, you count a word, then you get count. For each word is counted 1. And then you want understanding for each count how many words, right? So the final result is 1, 3. It means the word appear once, there's only 3 words, hello word, bark. The word appear twice? No. The word appear 3 times? No. The word appeared any time, other times except 1? No. So only 1 result. Only the 3 words appear once. That's a query. So that's the first line showing the query and the result, how it looks like. So when you turn over your page, the second page only has another word, hello, right? So you say another hello. So you have to updating the count. Once you update the count, the hello count jump from 1 to 2. Then on the final result, you have 2, 1, right? Because the word appear twice has 1, which is hello. But the problem comes. The word counted 1 is not 3, it should be 2. How does this happen? So this is a difficult scenario where you have to refinement. In the previous example, we just updating the same row. In this case, it's difficult because you are not only to just updating 1 row, you are retracting another row. So the result input changing affecting 2 rows, not only 1 row. So this is very complex. How to solve this problem? We need to introduce in retraction. So instead of just updating, sending accumulate result to the final table, you have to do the retraction. Basically, you tell the final result that, okay, there is a number 2 and the result 1, but you have to retract the previous result 1 to 2, not 3. The retraction good because it ensures the correctness, but it's not cost-free because the event here is doubled. You send 2 messages instead of 1. And another backwards is that some aggregate, let's say max and minimum. So those operators, when they handle the retraction, they very, very expensive. For instance, max. You just using keep as 1 value, but here you need to keep the whole history because when the 1 value retracted, you might need to find the second top as a max. So you cannot just keep 1. So max retraction is very expensive. You keep all the data. But the good thing is we do this by SQL engine. Remember SQL engine I mentioned has an optimization framework. So in SQL engine, it can automatically detect the scenario where operator needs to send a retraction, where it does not need, and the operator need to handle or not. So the goal for the SQL engine is to minimizing the retraction to get the best performance. And the good thing is that the user never care about reading about the retraction. They don't know that. They write a SQL for streaming case. They want to have the same result as the batch processing. That's it. So the SQL engine handle everything for you. You just write SQL, and the SQL engine will ensure the correctness. Okay, so I have explained why the ANSI SQL makes sense for the stream processing and introduce the dynamic table and the retraction. With dynamic table and the retractions, the semantics of the SQL for the streaming is complete. You will have the same result as batch processing. Okay, now I introduce how the Flink SQL engine, how it looks like. This is history of the Flink engine. So Flink start off with Flink, Apache Flink. And we made a lot of the improvements. Basically, we released Flink 1.0. It's an enterprise edition of the Flink with a lot of improvement. More specifically, it's focusing on the scalabilities, performance, and the functionalities. We recently released Flink 2.0. So once we solve all the streaming problem, we realize that the engine is powerful enough to support all different other scenarios, including batch, OLAP, machine learning, and graph. So Flink 2.0 is a complete engine, unified high-performance compute engine for complete data applications. So this is architecture. So we achieved the goal that one single SQL query with different mode, either batch mode or stream mode, has the same result. And we unify the pipeline for the batch query and the streaming query. So we implement the query processor, including the optimizer and the executor, and have unified the runtime. We did a lot of modifications. And here's how it looks like inside the query processors. SQL and the table API translate to logical plan. Once it has a logical plan, the optimizer will select the best physical plan and then select the proper operators. Those operators comes up with the execution DAG. So we observe that after we do this, the SQL and the logical plan is completely the same for batch and the streaming. And because streaming need to handle some difficult part, either state or retractions, it has some unique plan. Then for the optimizer, physical plan, execution DAG, there's a lot of difference. Okay, here's a Flink SQL functionality. I want to emphasize that the streaming processing with Flink SQL, now today, we can pass the TPCH with 1T, 10T, 100T. And the results are same as batch processing. It also passes the TPCDS. The exactly same query as batch. The streaming processing with Flink SQL follows ANSI SQL. That's what we originally proposed, the goal. We're aiming to let the Flink SQL follow the ANSI SQL. We achieved that goal at the beginning of the project. And it supports major data types and the 3 different user-defined functions, support all types of the join, over window, grouping window, different sub-queries, correlated, uncorrelated, and advanced analysis, grouping side, cube. All those functionalities make the Flink SQL engine pass the TPCH and TPCDS. Okay, that's a brief introduction about the Flink SQL engine. Now I introduce the Flink SQL optimization works. As I mentioned earlier, so the SQL and the logical plan for the streaming SQL. It can sharing completely the same as the batch SQL, but the optimization, the physical plan, has some different comparing to the batch processing. So here is my observations. So most of the optimization rules, I would say 70–80% of rules, streaming can share with the batch, prediction, projection, push down. And for some rules, like joining reorder, it shares the same philosophy as the batch processing, but it has different way to collect the stats. Batch need to scan the whole table, get the stats, and the streaming has more opportunities. It keep updating. If you have the hot update, when you're understanding the streaming data, you can hot update your job graph. But there are some other major difference. Those difference, first of all, the sort-related rule for the batch, it does not have for the streaming, right? In streaming, nobody wants the sort, because if you want to sort a result, streaming process the record one by one. If you want to sort, that means whenever a result comes, you sort a whole lot of data, all the history data. It's causing a lot of retraction and a performance problem. And some other different unique design for streaming are majorly three. One is the state. The streaming needs a state to handle the failover. So state has different design, map state and value state. And map state is expensive than value state. So optimizer need to find the rule to make sure the state is a value state instead of map state. And as I mentioned earlier, streaming need to handle retraction. So optimizer also need to smartly understand that. And then because we have the image SLA, user tells you the latency SLA. Once you understanding the latency SLA, you can do the micro batching to improve the performance in some cases. That's pretty much the optimization concept and opportunities we have observed for the stream processing. And there are some others for the execution, including code gen, smart memory, and smart I/O processing. Okay, now I use some example to go through this, because I understand this is really hard to understand. Go each design deeper. We need to look at the code, but doesn't make sense for the presentation. So I just using some standard example to explain why streaming SQL has those challenges and how we solve this. First, let's look at the TPCH sorting. So what TPCH sorting does? TPCH sorting, it joins two tables. One is the customer table, one is the order table. It joins two tables, and it's using a contact to count those jointed the customer, the total order for those customer. For the batch processing, it understands that the customer table is much smaller than the batch table. The order table. So it buffers the customer table and let the order table streaming join to the customer table. So this is very standard. It's hash join. But for the stream, we cannot buffer one table and then stream another table, right? So streaming is live data. You keep receiving data. You have to save all the data into the state. So basically, whenever data record comes in, you save to the state and look into the other state. If it exists, you join and emit out. If it does not exist, it will save in its own state. So the challenge here is you need to keep two states, and you're processing the data one by one. For this case, the customer PK is customer ID, and the joining key is customer ID. Then you just need a value state, because for each row, there's only one value. But for the order, you cannot using value state. You have to using map state, because for each customer, it might have different orders. So map state is much more expensive than the value state. Usually it's 10x slower. So that's a bottleneck. So how we improve this? We utilize the aggregate and the join transpose rule. So we let aggregate transpose under the join, push down the aggregate. Once we push down the aggregate to the order, so order will group by the customer ID. Once we've done that, for the streaming case, the joining, the right-hand side, the state is changed to the value state. Because you're grouping by the customer ID, joining key is grouping the customer ID. And you just pre-aggregate everything. And the state only for each customer, you have just one value, which is a count for this customer. Once you've done this, amazing thing happened because the map state disappeared. You have a 10x improvement for just searching on this state. We actually got 25x improvement for TPCH sorting. So this case is not just only for this query. It's applied to all the queries. Even if I remember correctly, TPCH 14 can apply this for the streaming. So once we've done this, the streaming performance is very close to the batch processing. I will summarize more, but yeah, that's what we observed. Okay, another example, TPCH 15. So what it does, it's reading all the items and do the aggregate. It sum the items values, certain values, and finally it finds the max values among all the items. Remember I said the example retractions, the word count. This is a similar scenario because when you do regrouping, the second aggregate need to keep all the data as a max retraction. So this is very, very slow because the operator on the max aggregate need to keep all the data. But in this case, it's very lucky. The input is unsigned type. It's not negative value. And once it passes some aggregate, the value actually keep increasing, ascending, right? Then we derive the property for each column. It's called collation for each column. Once you understand in data trending, it's keep increasing or decreasing. Once you have those information at the final aggregate, the max aggregate, knowing that it will never retract back, then we are safe to make the max retract as a max. So this improved this entire query as 15x. Another amazing thing happened. Also, such kind of improvement can be applied to all other TPCH, TPCDS queries. Okay, those just some examples to explain for the streaming cases. Those are not happen for the batch at all, right? So this is something new, completely new for the entire SQL engines optimization framework. Okay. Now, finally, I use two examples to explain in stream processing how we handle the data screw. Imagine you have an aggregate. You're grouping by the color. So red color goes to one aggregate, purple goes to another one. If in the entire job, the red color has huge amount, significant more than the purple, the aggregate on red will quickly screw up, will quickly buffer it all, and then back pressure the entire computation pipeline. You get very bad performance. One way to solve this is that we do the micro batching, and we also do the local global ag. We do the pre-aggregate. For each source, we let the local aggregate do the pre-aggregate. Then you quickly have all the data reduced. And the final global ag will have the balanced the data throughput. So this usually can improve the performance to 10x easily, 20x. So this case is lucky, but not every case you can reduce. For instance, count distinct. So count desync not grouping only by one key. It also desync on another key. So those two keys together give you less chance to reduce. So local global egg will not work in this case because you reduce only a few data. You have to do the local global egg smartly. In this case, instead of change the source and the local egg, you do the regrouping. You first group by the distinct number, and then do the global egg. Then you quickly get the performance improved. Okay, this is performance tuning we learned for the stream processing from top to bottom. Query optimizer with different plan. It has 10x, 100x, even higher improvement. Query executor, smart design. Your functions, very efficient function can get you 10x improvement. And if you have dedicated, which we have, dedicated state engine, it gives you high throughput, lower I/O high throughput. The runtime OS tuning can less than 10x, but the good thing for the runtime tuning, for example, any flow control, it can be applied to the globally. It affects all your jobs. Your entire cluster will have lower CPU. And then the resource comp. If you do the auto comp smartly, you will have higher performance. With Blink engine, we have Blink platform. In this platform, we call it Ali Cloud Stream Compute. It processes hundreds billion records per hour. In this cloud, in this cluster, in production, we have thousands of the customer streaming apps. And the largest app has actually 5,000 subtasks and tens of terabit state. This is our skill. And I think I pretty much finished my talk. And those are takeaways. In this talk, I want you to know that, first of all, streaming processing can be described by the ANSI SQL with dynamic table and the retraction concept, semantics, right? And the Alibaba Blink SQL follows ANSI SQL. It passes the TPCH and TPCDS. And the SQL optimization for the stream processing faces new challenges and opportunities. If you look at currently big data processing, most job still batch processing. From my point of view, the reason is that batch processing is less expensive than the stream processing. The user doesn't know the difference. We know. So we keep improving the stream processing. We see it's closer to the batch processing, except the joining, because joining is expensive for the streaming. But most other cases, stream processing is less expensive. Because batch processing, you also need to, most cases, you also receiving the stream and save to a batch file and then do the processing. It doesn't make sense. From my point of view, in the future, it takes years, but in the future, once we have the very powerful streaming engine, the performance streaming engine, then all the job will switch to the stream. And our platform operates the world's largest stream processing business. Thanks, and questions? Yes? Yeah. I think better to use the microphone, yeah.
So your optimizations for not having to do things like max with retract are fairly specific to a query. So how much guidance do you have to provide to a user of your service? It seems like it would be very easy to accidentally write a query that would reduce your performance by 25x. So how much guidance do you have to provide, and is it fairly easy for a standard SQL developer to pick up and write on this without accidentally writing very inefficient queries?
Let me try to understand. So you're talking about the retraction improvement. We got 25x improvement, but you're saying how easily it can affect other queries, or what is it? Oh, long.
Right. So.
Oh no. Yeah, I got it. So it's not specified just for this query. It's it's standard. It's all segmented. So that means if you have a big queries, it also can improve.
Right, but I mean, so if I write an aggregate which has a max over a sum, then your optimization will work. But if I write my query in a different way, I could be collecting kind of the same metrics, but write it in a different way where this optimization won't apply, right? So how much guidance do you have to provide to a user to make sure that
what do you mean the guidance? The guidance means hints, or what? So I'm trying to understand what you mean by the guidance.
So yeah, so you have a user which comes along and is used to writing batch SQL, right?
Yeah.
Writing any type of aggregate,
Let's use the example as a TPCH, TPCDS. So TPCH, TPCDS was used to design for the batch. We didn't change anything. We just run it in the streaming mode. So we didn't give any hints, tell it's streaming. So we just designed the SQL engine, it understanding the scenario, and improve the performance.
So I guess what you're saying is that in practice, almost all aggregates are already written in such a way that your optimizations work?
If it hit the rule. So we have a specific rule. It's like a batch query, right? Hundreds of rules. So those rules are orthogonal. So whenever it's needed or it works, then it will take the rules and optimize the plan. Then it affects all the queries.
Right. So, but the rules in streaming are different from the rules in batch, right? So if you're used to
80%
writing,
the same, and 20% are different.
So if you're used to writing batch queries and you're used to working with the optimizer, then you might write queries that are very inefficient for streaming, right?
Right, exactly. So
do you try to educate your users in any way about
this?
No.
No. User doesn't know in that. So the engine is closed. So it's a black box. User just write queries. The engine smartly knows the queries. So we only let user config it's a streaming mode or the batch mode.
Right.
So once we know that the 80% of the rule is shared by the batch and the streaming, and there are some specified streaming rules. Yeah.
Thanks.
But that's very good. We are going to post more blogs and even considering open source this. So it won't be very long. Hopefully this year. Yeah. Thank you for the question.
Can you do more complex? I mean, I've heard Flink and Spark are kind of competitors, but I don't know. I mean, obviously data frames is, but you can do even more stuff like MLlib and different things like that. Is Flink just like a SQL engine for Flink, or are you going to eventually get into that kind of stuff with Flink, or what is your?
Inside Alibaba, we are already exceeding the open source Spark, but we did not open source yet. We are considering do that. So it's not just Flink 1.0 is enterprise version as Flink, you can understand. But Flink 2.0 is complete huge engine supporting batch, streaming, OLAP, machine learning, and graphic. So we consider to open source those gradually. I think the first step is batch and streaming.
Sorry, one other question.
Go ahead.
Okay. What's your underlying data structure? I mean, obviously streaming is in memory and that, but is this only streaming and only processing, or are you actually able to do these same queries against, say, HDFS data systems?
Yeah, exactly. We support all kinds of the file system and connectors. Yes.
I'm just wondering, like, once Flink 2.0 is going to be in Apache, are you guys going to push maybe DataWorks also brings that under its own umbrella? Like, like Flink's not, like, for example, if you're an HTTP customer, Flink's, you don't get Flink.
Yes.
Yeah, that's a package.
Yes, exactly. Yeah, we will plan let everybody have, for example, DataWorks notebook will support the Flink. We will try to do that. So basically, we want to release this powerful engine for globally user.
But Flink now has been renamed to Blink. Is that what it is?
No. Flink is still Flink. It's Apache Flink. Okay. The Blink is starting with Flink. We did a lot of improvement. We cannot merge it back. Yeah, it's so many differences. We were trying to do in the last year, but we realized we have a lot of, but yeah, it might be. We haven't had conclusion yet. But right now you can consider it as two different projects. Yes? Can you use some phone? Sorry, speaker?
I'm just curious to know, so why did you choose Flink over Spark streaming?
Comparing the Flink streaming and the Spark streaming?
Yeah, so your engine is on Flink. Yeah.
Okay. I think I mentioned that either Spark and Kafka, they support SQL, right? But they are not ANSI SQL. So the major problem, for instance, if you want Spark streaming running on TPCH, you won't get through. They can only support 4 queries because they don't support retraction. So when you run a Spark, you need to handle each state and merging the difference. So the retraction is not supported. The retraction is only supported by Blink and Flink. Flink we contributed back. That's a major problem. You cannot using the batch query for those kind of things. Yeah. All right, I got it. I think that's it. And if you have questions, we can talk in the corner. Thank you.